Hello everyone, welcome back. In the previous lesson, we saw two methods for making alcohols from alkenes. The first was called acid catalyzed hydration. This is where we use a concentrated acid, such as sulfuric acid or phosphoric acid, to make an alcohol from an alkene. A couple of things that were notable about this was it involved Markovnikov addition, right? So Markovnikov addition, meaning the OH hydroxide group or hydroxyl group was added to the more substituted carbon. It also involved the formation of a carbocation intermediate, which meant that rearrangement was possible in some, depending on the substrate. Okay. The advantage of this is that it is definitely the easiest one to do. We even did it in our lab whenever we made cyclohexanol from cyclohexene. Most of you had pretty easy success with that. The second one we learned was oxymercuration, demercuration. It's a two-step reaction, first being oxymercuration, followed by demercuration. This was similar to the first one, or to our acid catalyzed, that it is Markovnikov addition, but it does not allow for rearrangement because there's no carbocation that forms. Okay. In terms of the chemistry, these are very similar. This simply doesn't allow for rearrangement, which can make it useful if rearrangement would have been a problem. One side note, this does produce Hg, mercury, as a product. Okay, mercury is not an ideal product due to the health risks associated with it, so it's not common in high school lab or even a college lab. But again, you might find that rearrangement was a big problem. This would avoid that. The third type that we're going to look at today is called hydroboration-oxidation. This, unlike the previous two, is anti-Markovnikov. Okay, meaning the OH group will be added to the less substituted carbon, which makes this ideal for making primary alcohols, whereas the previous two are not very good for making primary alcohols. So let's look at this. This is a two-step reaction, the first step being hydroboration. So let's look at an example. Okay. All right, so this step requires, in addition to our alkene, borane. You hear that that suffix "ane," like an alkane, but instead of being made with carbon, it's boron. Borane is a very reactive gas, not so reactive that it would actually can combust in the presence of oxygen. So it's a tricky one to use. And another one that you wouldn't use in a high school lab, but probably not even in most college labs unless you were, doing graduate studies. Now this would be dissolved in tetrahydrofuran, which allows it to form a more stable complex. But again, still precautions need to be taken when using this borane and hydrofuran. So this would be dissolved in some non-reactive solvent like diethyl ether. Okay. B, boron, is actually a nuclear term. Sorry, it's actually an electrophile. If we look at BH3, this is a common compound that's taught in general chemistry classes because it's unusual. It's unusual in that it doesn't have a full octet. Okay, it has room for a lone pair to be donated to it. Lone pair acceptors are called Lewis acids, and you can also consider them electrophiles. So borane matches this definition. All right. So let's look at how this could react with something like propene. Propene's a simple example of an alkene that would, in Markovnikov, hydration would form a secondary alcohol. Let's look at how it works here. Propene. I'm going to try to show some stereochemistry here. Here's our double bond. Again, using my wedges. Okay. All right, so here's my propene. Here's my borane. Okay, borane is a trigonal pyramid. Okay. So like I said, borane is an electrophile, and it can be attacked by the double bond. So one thing I want you to note is that boron could be added onto either of the two carbon in the double bond. Okay, but whichever one it does, I'm going to draw this out. Whichever one it does add to, the other carbon is going to be left electron deficient. Okay, so let's give it to, okay, suppose it were to bond to the right one. Here's my boron, hydrogen, CH3. Okay, when boron starts to form that bond with that carbon on the right, the carbon on the left starts to lose some of its electrons, become partially positive, while the boron becomes partially negative. Remember, the partially positive charge is most stable when it's on the more substituted carbon. So this boron, it's energetically favorable for it to add on to the carbon on the right in this example, the less substituted carbon. Okay, this reaction would finish with hydrogen bonding to that partially positive carbon and getting kicked off of the boron. Okay. So this is our intermediate, ends up forming a stable alkyl boron compound that would look like so: CH3, hydrogens, so full carbon. This is BH2 now, and hydrogens. Okay, so effectively, the BH3 added across that double bond. One of the new hydrogens came from the BH3. The other two, or yeah, and the BH2 is all that's left. Okay. Finally, or not finally, but subsequently, that BH2 is still an electrophile, and it could react with additional alkenes. It could react a few more times because it still has two hydrogens left. I'm going to try to draw this a little simpler so you can see what that would look like. Skipping the mechanism part. This is what happened in the first one. Propene react with BH3 to form this, I guess you would call it a propyl borane. Right? But we could continue to react that with more propene. The next one you would get would be dipropyl borane. And we could react that with an additional propene to make our final product, tripropyl borane. Okay, so tri-substituted borane, in this case tripropyl borane, was made from 3-propene reacting with 3-propene molecules. Okay, so we call this an alkyl borane. Right, and they're formed in that first reaction, called a hydroboration reaction. They're not very stable. They can be easily oxidized or reduced. So we're going to look at how this could be oxidized to form an alcohol. We're going to kind of skip over the mechanism for this, and I just want to focus on the final product that forms. So I'm going to rewrite this molecule for the rest of this lesson. I'm just going to replace the propyl groups with R's. Okay. We got R3. Right. So alkyl boranes can easily be oxidized using an oxidant, and a very good oxidant is peroxide, hydrogen peroxide, H2O2. Now H2O2, when in the presence of a base like sodium hydroxide, actually forms a pretty good nucleophile HO2. And I'm kind of going to gloss over the mechanism. If you want to see the mechanism, you can see that in section 8.8 in your text. But the end result is that the three alkyl groups bonded to the boron end up substituting that boron, that RBr or that CBr, sorry, not that CB bond with a OH bond. Looking like this. Okay. So the boron in these molecules simply ends up getting replaced with an OH group, forming alcohol. Because boron was added to the anti-Markovnikov carbon, the resulting OH is also anti-Markovnikov. Okay, so this results in this case, if R was a propyl group, this would make one propanol, which is different than what we would have formed if we used like acid catalyzed or oxymercuration, demercuration. Okay. One other thing we can do with these alkyl boranes is we can reduce them. Oxidation typically involves adding oxygen, such as adding an O in the OH. Reduction in organic chemistry generally involves hydrogen. So this can be reduced. Rather than using a base, we use a weak acid. In this case, that weak acid is going to be acetic acid. Okay, this simply reduces it to an alkane. So in place of the propyl groups would become propane molecules. Okay, one thing I kind of glossed over, and I don't think it's a huge deal, but one thing to pay attention to when we look at this mechanism, the hydrogen and the boron, they're both added on to the same side of the double bond. Remember what we call that when two atoms are added to the same side of the double bond? This is called syn addition. Okay, for the most part, anti or syn, it doesn't really make a difference in the final molecule that forms. After all, this molecule that forms propanol, it's not a chiral molecule anyway. But when we're talking about rings, it could affect a chiral center. So note that this is syn addition. So I'm just going to go back to the beginning so you can see there's three hydration reactions. The first two, acid catalyzed and oxymercuration reactions, both followed Markovnikov's rule, with the notable difference being acid catalyzed allows for rearrangement. This new reaction, hydroboration-oxidation, is anti-Markovnikov. It does not allow for rearrangement. There's no carbocation that forms. No rearrangement. Okay, it is syn addition for ring examples that could matter. They're both added onto the same side of the double bond, and it proceeds through an alkyl borane intermediate. Or actually, I shouldn't call it an intermediate. This is a stable molecule, but it involves an alkyl borane product that forms part of the way through. So this is a two-step reaction. So I'm just going to quickly write out how we could write this without showing all the mechanism. We could have, say, our propene, CH3. All right, so here's our propene. The first step involves borane and tetrahydrofuran. Okay. The second step involves hydrogen peroxide with a strong base, right? And this would end up producing a primary alcohol, right? Following the anti-Markovnik competition. If we were to do this similarly with, say, a strong acid catalyst, we would get anti-Markovnik addition. Okay, 2-propanol, right? So if you have any questions, please post them on Google Classroom. This section, the sections covered in here, I believe were 8.6 through maybe 8.9. So you can also check it out in your book. All right, thank you. Have a good one.